Thank you to Mel Science for sponsoring this episode of the podcast. Mel Science is a subscription service that offers monthly science boxes, which combines hands-on experiments with VR and AR technologies to engage all of us in studying science. They strive to make studying serious science accessible and mainly look cool as well. So in this particular episode, we have got the Hydrophobic box, part of the physics science kit. So this is just one of the kits from the physics module. They actually have a physics kits, they have chemistry kits, as well as general science kits. So as you can see, or for the video listeners out there, we have a hydrophobic kit where when we put water on these three different materials, one of them gets fully absorbed, one of them gets partially absorbed, and the other, you can see the water just dangling on top. And for another experiment, we see some hydrophobic sand, and we see its relationship with the water, and we see some really cool artifacts in the water. Once we try to dip that spoon in and really try to get that sand out, we just see a powdery surface coming right out. So it's some pretty cool stuff. Again, just one of the kits that they have out of many physics kits. So go check them out. For all of those listeners that are listening to this, you can go click the link in the description below or type in the code MP50 or scan the QR code somewhere on the screen here for a 50% discount. That's half off your first month of Mel Science boxes. So why don't you check it out, see what's up, and enjoy the episode.
It's the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray. And we welcome you back to episode number 107, where today we are going to be talking a little bit about what we did in our summers. I think it's been quite a long time for those of you that are, rapidly keeping up with us. Quite a long time since we posted. So what we did in our summers, some quite fruitful experiences as compared to what we do in school. So I think we're going to talk a little bit about that, what we have prepared for our final year of school.
Damn.
Ooh, that's crazy. Final year of undergraduate school. Or no, I shouldn't say school, yeah. Undergrad. For sure.
Mm-hmm.
So, yeah.
It feels good to be back on the podcast. Sure. You might have noticed. I know I received a DM yesterday. I think his name was Jacob. He was asking where we were, and here we are. No, we definitely took a break. I think it's a mixture of being busy with like school related things and also life relating things.
I think last month was mainly life relating things because, especially for me, it was kind of like the whole month was a month of vacation, so I had a lot of fun. So it was kind of like before our final year of school, just wanted to get it all out of me and then come back. So we literally almost didn't have any time to record because it was mainly my fault. So there is someone to blame. But yeah, it was basically both of us, though. It was life getting in the way as well. Yeah. So we just let summer be summer. Maybe the podcast can also take a break once in a while,
I guess.
You have seasons of podcasts and stuff. That happens.
Oh, yeah.
So,
season 2 right here.
Season 2, right?
Season 2 is starting.
No, this is like season 3.
Well, it's the only break we've taken.
The only break. Yeah. Okay, so I thought you meant like year by year, but yeah. So I guess season 2.
One thing that's interesting though is that we started the podcast after our first year of university. So I wonder, like, if you were to listen to us talk as first years, technically, like, do we just sound dumb, compared to now? Because I feel like if I were to talk to a first year, I'd be like, like, there's probably a better way to explain that. I feel like any explanation you give as a first year, there's probably a better way to explain it, with like the mathematical knowledge that you gain.
I just think you just know so much more. Yeah. But it kind of depends on the first year. There are definitely some first years.
That is true. But, I'm talking about like me and you.
Yeah. Well, okay, me and you. Yeah. We've definitely come quite a long way. Yeah. We've definitely come quite a long way. Also, bro, your volume is. Oh, you might want to lower that a little bit.
I think I'm just close to the mic.
Okay, fantastic. So yeah, I think if we spoke to our first year selves, we would definitely maybe not appreciate, maybe not love us that much, maybe we'd be like, yo, get in your lane. Because I think we definitely thought we were that much.
No, I don't think so.
No?
I thought, no.
Because again, as I keep saying, I always thought I was smarter back then than I am now.
Oh, I don't think so.
Because I know so much more. How much I don't know, I keep saying that.
Yeah.
But yeah, so...
Yeah.
That's it.
Anyways, you might have noticed that we are sitting on a couch right now. If you're watching the YouTube video, I know a lot of people just listen to us, but for the visual consumers out there, we're not sitting at a table. We're sitting on a couch. Mm-hmm. Why? Mainly because this is how our living room is set up now.
Oh, yeah, we're in a new place now.
We're in a new apartment.
Because our last episode was online. It was on Zoom.
Yeah, it was.
Yeah, so we're in a new place now.
Yeah.
So
now we had our couch here, so we said, you know what? Let's just put the cameras up and sit down on the couch. It's nice, it's relaxed. Because I think I like it, to be honest. I don't think it has to be this whole like looking. I mean, if we have our iPads here, so it is what it is.
Because we would have to severely rearrange.
Yeah.
For
other than that, you might notice right here that there is a piece of merch that I'm holding in my hand right now. Okay, we get it. we get what you're gonna say, but here's the thing. I wrote down in my schedule, in my agenda, that on Saturday we're gonna set up the merch store, and we're definitely gonna do it. We have to go to the bank. We have to do stuff at the bank to connect the bank account, all that stuff. We're gonna set up the store and we're gonna publish it, and we're gonna let you guys know that the merch store is up and ready for orders. Yeah. Other than that, I think we can get into the podcast now.
Oh wait, we forgot about.
Oh, yeah.
Comment, well, not of the week anymore, but comment of the episode.
Comment of the episode.
So last episode was History of Physics. A lot of people were asking for that. So we had a lot of fun researching. Yeah. A lot of fun
that was a really popular episode, by the way.
That was a really good... Look at that volume, bro. I'm saying you might want to turn it down just a bit. I'm saying I've been seeing some sporadic volumes. Sorry for that. But yeah, so definitely a fun episode to record. It's a fun episode of research. It was Faraday and Tesla, for those of you that didn't catch the last episode. And so the comment of the week is kind of related to that. And Sid Sachdeva, they say, I've been waiting for this episode since the first History of Science math series.
Let's go.
I can't wait to start my astrophysics journey in like a month. So I'm assuming he's going to college in a month. Thank you guys for reigniting my physics fire.
Nice.
Thank you, Sid, for that lovely comment, and you're very welcome for reigniting that fire.
That is the whole point of the podcast. It's just to have people go and find all of the mistakes that we made and learn something on the way.
Well, I think that's a beautiful way to summarize it.
You hear something that we say and you go, that doesn't sound right, but as you go and research for yourself, you learn something, which makes you in turn smarter. So.
I think I was talking to either Parker about this or someone else about this the other day, and I was literally just thinking that, or I was telling them, like, the main purpose of even like our History of Physics episode, like, we don't go, like, when we talk about the episodes and the experiments and whatnot, it's still, we do go into the level, but like, it's still very much just getting you interested into what they actually did, for example.
I think the best part of the history episodes is that it provides, because we do this in class, like our professors present the physicists that came up with the ideas, and it just provides a context as to how we came up, or we as within history, how the physicists before us came upon these ideas and these theories, and then now we're here.
Yeah, so I think it definitely gives you that perspective. But apart from, and add on to that, it definitely tells you, hey, now that they're talking about this experiment, because actually I was re-listening to it and I'm like, hey, I kind of want to research more on this myself. And I'm like, this is the entire point of our podcast, to listen to what we're saying and then be like, oh, wait, I want to research more on this topic. Yeah. And then, wow, you're educated.
Yeah. Because there's no way for us to talk about something and paint the full picture. There's no way.
Right.
All we can do is introduce at most. Mm-hmm. So that is what it is. In other news, we have a bunch of downloads and followers. That's it. I don't have the numbers.
The way that you said that, we have 615,000 downloads.
615,000.
So it's really cool.
Slowly getting closer to 1 million. On Spotify, we're at like 31,000 something followers. we recently I mean like maybe in the past month,
Yeah.
we reached 5,000 on Google, like 5,000 followers on Google. So shout out to Google.
Thank you for following us wherever you're following us and listening to us, wherever you're listening to us. If you want to watch us, come check out our YouTube.
We're going to start posting more. And I had an idea. I didn't even tell you about this, but I had an idea, like, because posting podcasts like these nowadays in our 4th year, we have a lot of projects and assignments and time-consuming activities. We can try making like different formats of podcasts, like maybe shorter form podcasts, maybe like some more creative ideas in presenting like content.
Maybe we can do like quick facts in physics,
something like that.
Like,
well,
your weekly facts, I don't know, something, or I don't know, like, maybe not facts, maybe like
like a 30-minute episode about something quick. Who knows? Anyways,
could be many things.
Anyways, this is just an idea right now.
Ideas spitting out. Yeah.
So, this summer, I was actually part of the summer undergraduate research program at the University of Toronto / David A. Dunlap Institute of Astronomy and Astrophysics, which is just the name of the department here at U of T. And so basically, I got to pick out of like a list of projects, and then I landed on one, and I got to do that for the summer. And this episode, I will be describing exactly what I did all summer, because it's pretty interesting, actually. I really enjoyed my summer. I got some research experience. I got to do some fun things in the department, and there was also a whole bunch of like not events, but like they would give talks specifically for the summer students. It was really cool. A really good learning experience. Yeah,
because you did a whole course, didn't you? Like you did a whole course in the beginning.
Technically.
Right.
So
it's pretty cool.
Yeah, as a summer student, they offer a course in computational astrophysics before you start your research, and it's a 2-week course. And you go in every day for 4 hours, and you do computational stuff. I don't remember exactly what we did, but there were a bunch of units. I remember one unit was on machine learning, one unit was on Fourier transforms,
like FFT.
Yeah,
like
stuff
fast
like
Fourier
that.
transform.
One unit was on. There was like also the basic stuff like plotting with Python. All that stuff.
For some reason.
Also, GitHub. We learned about
GitHub is so important for like everybody. By the way, this is like a shout out to GitHub for everyone listening here who doesn't have a GitHub.
Oh my God.
It's very recommended to either understand how it works or, to have one yourself, first of all.
Yeah.
Because it's very useful to, be able to, access it, number one. And number two, it's such a shareable item, It's like the first thing that you would want to do when you're like, hey, check my code on GitHub.
It's so important, especially if you're doing an actual like real life project with people. It's so universal, right? You have this file on Git, and you can do like branches and stuff and add different features that won't affect the main code, and it's all like, it's such a perfect way.
Yeah, no, but it definitely gets confusing. It definitely
definitely.
Like, I haven't really gone all the way through GitHub, but like it definitely gets confusing with like Origins. No, not Origins. What is it? Is it Origins, or like is it like what is it called? Like the different, I don't know.
Branches?
I guess am I talking about branches? I guess. Again, I don't even know the names for them, but like if you show me like a console, I can probably do it. Yeah. But it's just so much to know that it's really good if you learn it on the side, because again, it's very good for collaboration and whatnot. So definitely good tool to have. Anyways, continue.
And also, if you already know GitHub and you're trying to do research in the future, people appreciate that, right? Like, you go up to a supervisor and you show him your your CV, and you can also send him or even put a link to your GitHub to your CV.
Yeah, and that's why, it's such a good thing, especially for professors, as you were saying, or anyone really who's either looking to hire you, looking to take you under for research, they're looking to take you anywhere. It's just a good thing to have because now they know, number one, either you can use it, and number two, hey, you have your own. So it's always a plus.
Especially if it looks good too. If your landing page on GitHub looks good, it's just like, wow, this guy knows like what he's doing.
Yeah, no, for
and
sure.
That's a good impression.
A good GitHub is a good person.
Definitely. So yeah, we did that during the course, and I learned a bunch of skills. One cool thing that one of the assignments that I did was actually producing the Mandelbrot set just from scratch.
That is cool.
On Python.
I think you showed me that, right?
I did show you that.
Yeah,
it was really cool. Another thing was plotting the Lorenzo tractor on Python from scratch. I
forget what that was.
I did. You know the butterfly?
Oh, but so explain this to a little bit. Like what did you do to plot these?
Okay, well the Lorenzo tractor, it looks like a butterfly, and in short, it's a demonstration of chaos, because essentially, if you know anything about chaos theory, the initial conditions of it's a set of differential equations.
Okay.
I think it's 3 differential equations, and depending on the initial conditions, your trajectory will change a lot, very much. And it's an unstable, or it's a stable solution with 2 stable nodes. And it's very, like, the behavior is very, very interesting, and it's a very famous problem in computational physics.
Well, I'm getting into it.
It's actually the original where it came from was atmospheric physics, basically modeling how the air flows in the atmosphere based on like the gradient of the temperature and things like that. Yeah. But now it just looks really cool. Veritasium has a video on it as well. So if you want to go, I think we've spoken about it as well. Anyways, we did that. And the conclusion to that course was picking like a mini project and doing the project and writing a small report. I did a project on analyzing trends in astrophysics. And it was quite interesting. I got to deal with a package. I forget what the package is called, but
TensorFlow.
No.
TensorFlow?
No, I didn't. TensorFlow's a like neural network machine learning.
Did you do ML though?
No, not during the summer for my project. It was a package to query a database.
Oh, SQL.
Yeah, well, SQL is like a type of query, but
you're talking about the package to use that?
Yeah.
Oh, I don't know.
And essentially, I came up with. I wrote my own Python package with functions that can help you analyze trends.
So cool.
And that was cool. It's a little bit. I would have to show you essentially to describe my project, but.
So what are the trends that they?
Well, relating to my project, I analyzed the relationship.
What's your project, mate? You haven't said that.
Well, I'm going to get to it.
Okay.
But it has to do with ultra diffuse galaxies. And so I looked at the rise in popularity of certain terms that show up in papers that were published over the years, and how the use of dark matter and the use of ultra diffuse galaxies in abstracts or titles of papers show up, and you can see how there's a correlation between those 2 terms. And in the 50s, there was not a lot of use for dark matter because it was just coming up as a subject. And nowadays it goes up. It's kind of like a little exponential, and there's some interesting behavior going on there. But yeah, right after that course, boom, I started my research. So I actually worked on a project called the Dragonfly Telephoto Array. And it's essentially a telescope made up of 48 cameras, I guess, with telephoto lenses. And there's a scientific reason that is not really important, but the gist is that the telescope performs really well at capturing low surface brightness objects. And it actually, it turns out that images that are being produced by the Dragonfly Telephoto Array are able to capture galaxies that are ultra diffuse, which means that are super, super low in brightness that we have never been able to see before. And more specifically, it captures images in the visible area of the electromagnetic spectrum. So yeah, that is the project I worked on. What did I do? Well, the first thing that I did, I got started on working with the image stabilization inside of the individual camera lenses, because what happens is that we have these modules, let's say. Each module has 24 camera lenses attached to it. And that entire module rotates together to keep track of an object, because overnight, if you take long exposures, the galaxies in the sky and the stars that you're looking at will rotate because the Earth is spinning. And so to keep track of the object, the entire module rotates against the rotation of the Earth to keep things stable. Now, however, these cameras are mounted up onto this module, and the mount is made of stuff. It's made of material, metal, plastic, all kinds of parts. And these things tend to bend and flex and move. Even if it's very small movements, these can be captured in the images as very diffuse photons are coming in from space and into the lens. Even a very small little tilt, a little bend will change how the image is being captured on the CCD. Sorry. And so inside of each lens, each camera lens, there is a single lens that moves translationally, which translates the image that is being absorbed, I guess, onto the CCD. And that is what we use to stabilize the very microscopic changes that can arise in just the telescope existing in the physical world and materials bending and moving and unpredictable events happening. So that is what I worked on. The first thing I had to do was use Python and work with like very small computers. They're called Raspberry Pis, which control the actual lenses. And I had to go in and figure out how to take pictures. I had like a little setup with one camera lens in the lab. I got to take pictures and display them and figure out how to do continuous display of images, because if you're trying to figure out how an image has moved, you need to compare, right? Image 1 to image 2 and see how the objects have moved and how you need to correct for that movement. And so we need a continuous display of images. And then after that, it's about finding the features in like easily trackable features in the image and then tracking them throughout the exposure, and then taking your translational lens and moving it accordingly such that the image will appear to not move at all during an exposure. So yeah. I need a sip of water real quick.
Oh, I got water right here. If you want.
I got some.
Yeah, that's really cool, man. I can definitely see how that's very useful for sure. As you were saying, you're helping, stabilize the image literally. And now you can obviously, now that you did this with one lens, you can do it with
exactly
all of them. And then voila. Exactly. But is there an issue when you because I'm assuming
there were lots of issues.
That's what no, but when you add the other lenses, I'm assuming it's not as easy as just adding the lens and doing the same thing, right?
Well, it is actually. Oh. It is that easy.
I thought there would be some other...
Because the way that an image is compiled from Dragonfly is that all the images are taken from all the lenses. They are all reduced, and so their flat field correction is applied and all
so
that.
It's all like one image?
No, individually.
Okay.
And then the images are stitched together.
Right.
And that is your final image. And so you need to stabilize every single image as it's being exposed to the sky so that it's a clear image.
It gets into
and then you reduce it and produce a single image. So a lot of issues arose in this process. I didn't actually get to the like actually stabilizing images because there were errors that were out of my control that much smarter people on the team were handling. And so in order to be useful, I was put on a different task. And that task had to do with data organization and data visualization for the telescope. And this was the main part of the year, actually. I only spent about a month on image stabilization, and the other 3 months were spent doing this. Technically, you can also throw cloud computing into that basket. But yeah, I can talk about that later. Do you want to?
Sure, I can, because I can kind of talk about two different things. Because this summer was more of a little bit more of a relaxer for me. Wasn't much of a research driven summer. Still did things, but less intense. My last summer, I mean, not as intense as yours, but it was definitely a little cool because I've definitely spoken about it before. It's crazy that it's a whole summer ago, because I swear, like, it just happened. I've been thinking about it. That was like a whole year and some months ago. That's insane. Yeah. Anyways, so with Dr. Rastigu, actually,
who we had on the podcast.
I forget what was the name. It was a really cool name.
A theory of everything.
That was a really cool name. So we're most probably going to going to have him on another podcast to talk about the research we did together. But basically, yeah. So last summer was spent kind of doing some stuff with him. It wasn't really discovering many new things as much as testing things that were already there and kind of like, figuring out the best one, or almost which one is like most representative. But unfortunately, we didn't get to the very final part because as I was talking about it, he actually moved to University of Alberta. So he is no longer at York University where he used to teach. So, I mean, congratulations to him. But yeah, so there was like a bunch of stuff that happened in the middle, basically, and we couldn't really finish it. But it was still a little cool, so I can still talk a little bit about it. Basically, it was very, very, very computational to the point where the theory still goes to this day, still goes over my head quite a lot. Because the papers that I had to read for like my readings were like literally papers written by him and like his team. And I'm like, what are you giving me to read, mate? Like, I can't read this. But anyway, so obviously it stemmed from reading a lot of Google. Like that's actually how a lot of research works.
But actually, that's something that people know, right? Like if you're a PhD physicist doing research and you're dealing with undergrad students, that they won't understand a lot. And actually in class today, my professor, this is for like an astrophysics research course, my professor said that we're going to have to get caught up on the literature when we start a research project. We have to read like papers and reviews of things, and a lot of it is difficult to read. She even said, like, as a fourth year student, these are difficult to read. That's just how it goes. But just even not understanding really what you're reading, but just reading it and absorbing the material is a little bit helpful. Because you have to do it eventually.
Well, that's number one. But let me tell you why number two. Because a lot of times, and this like happened to me multiple times, like when I read like the really hard paper, and because again, as you very well said, they know it's hard. Like when they give it to you, and that's a big thing about research. Like you're starting to get into it, and sometimes you're like, damn, what am I doing?
No.
Like really, what am I doing? But then it kind of pieces itself together, and it's kind of coming along. So like it all kind of just adds itself up into one good piece of machinery after you've already gone through the little hardships. Because I feel like after you read it and don't understand it, and then like let's say you're talking to your professor about it, and then he says a few words and you're like, oh wait, I remember reading that word. And then you go back and read it a second time, and then you might Google something, and then you go back and read it a third time, and that's the power.
That's always how
Maybe
it
the fourth
goes.
time, maybe the fifth time, it'll be like, oh wait, this is kind of making sense. I understand why this is this, and that's the crazy, and that's like the crazy big revolution behind a lot of reading things that you don't understand, or just sometimes just like even watching things. I guess nowadays with YouTube, there are definitely some, let's say, advanced YouTube channels out there for a lot of people. And I'm sure if you watch some crazy physics videos, sometimes you're like, oh, damn, I don't know what they're saying. But watching it again, you might have a better idea. The third time might be even better.
One thing my Buddhism teacher,
this guy's in
said,
Buddhism class.
I have a Buddhism class. I had to take an elective, so
I was gonna be in that class, but it didn't fit with my class. It didn't fit with one of my required courses, so I couldn't.
Damn, that's tough.
Yeah,
but
that would have been cool.
One thing she said is that as a student, you need to understand that not understanding is part of learning.
Boom.
And so a lot of the times, you're gonna be in university. Let's say you're in physics. You're going to be in your physics class, just writing down what's on the board and not understanding a single word of it. And that's okay. Yeah. Because that is part of learning, just having no idea. Because if you already knew what was being told, then you wouldn't be learning. And what are you paying for then? You're paying to be perplexed and then to solve those problems within your brain.
You don't want to be told the answers.
Exactly.
Right? You want to be told how to get them, how to get there.
And my
TA, that's what people are for.
My TA for my electrodynamics course, he said, oh, I took a similar class when I was in undergraduate, and I knew, like, I use the same tech. Everybody uses Griffiths. He's like, I was also aware that there is a PDF of the solutions, and I used that PDF as well. And so all I have to say is that try not to just copy down the answers. 100%. And one thing he said is that as he was correcting or grading things last year, some students got 100% on the problem sets, all of the problem sets, 100%. And on the final, one person got 0. 100% on every single problem set, and on the exam they got 0 and failed the class.
Of course.
Literally, they ended with less than a 50.
No, but I'm pretty sure it's a requirement in that class to pass the exam, isn't it?
Well, I think they changed the weight because my exam this year is worth 70%. Which is crazy. It's the highest weighted exam I've ever had.
70% exam is crazy.
Yeah.
That's crazy. That's 350.
Yeah.
That's crazy.
Yeah.
That's insane. Damn, what were you talking about? We were talking about my thing, right?
Yeah.
Yeah. Where was it?
You said you were
I think we were talking about reading the complicated material. So, most of my time was spent reading complicated material, and most of the stuff that we actually had to do was kind of cool, actually. So, okay, I guess I can kind of get into it just like a little bit, because again, I don't really understand the theory, like really like the fundamentals, but I can probably just talk about it on a very easy level. So basically what we did is we were trying to solve for equations of motion of space, because remember in taking general relativity, we're saying that, hey, space curves everywhere, and given something like a black hole, for example, space curves around that in a certain way. So what we were trying to solve for was equations of motion around of space around black holes. And again, this is the part that I don't really I don't really get where we used a lot of these theories, but again, just the computation was mainly what I was doing and just finding different ways to do it. So it was not that much as in theory digging as I was doing, but it was mainly just understanding, okay, so we have multiple theories to describe the universe, right? They're all proposed. String theory is one of them. Another is loop quantum gravity. I'm sure there are others that I can't think of at the top of my head. Would you know other theory? Another kind of, I guess, a field theory. I don't know, like describing the universe. I'm sure there are others.
Oh, there's one actually that Roger Penrose came up with. And actually, it's pretty interesting because Albert Einstein said at one point and this is kind of a secondhand quote.
Yeah. He said, she said.
But he said that the physicists of the future will need to investigate a form of discrete mathematics in order to properly describe the universe. So that's what Roger Penrose tried to do. He tried to employ some type of like discrete algebra into this theory.
Wow.
I forget what it's called, but there's a funny name for it. And yeah.
Did it end up? I mean, I'm assuming it's still like one of the theories that is still like trying to be.
I think it's called twistor theory.
That sounds cool.
Twistor theory? Something like that.
That definitely sounds cool.
Something like that. Yeah. But it was incorporated into another theory that isn't super string theory? Is that a thing?
Superstring theory?
I don't know. It's just words at this point.
Theory? I don't think I could be wrong. I don't think I've heard that.
It's just words.
Theory?
I wouldn't know the first thing to describe that.
I'm not sure. I could be mistaken. But anyways, so like, yeah, lots of theories to describe the universe. And the one that my professor, Dr. Rastigu, was currently studying was loop quantum gravity. And the advantage, again, don't ask me these questions, but like these are just like things that I kind of know from what he said, is that, again, like I don't really know how a lot of them make sense, but like I'm just gonna say it.
Just say
like loop quantum gravity is like, because the whole issue, but like the whole issue between quantum mechanics and general relativity right now is that they like don't, is like, what's like the whole issue? Like you can't really bring general relativity down to quantum mechanics or something like that, right?
They're
like it's not really.
Inconsistent.
They're inconsistent in some measures. So
not inconsistent. It just doesn't
hold in some cases. Like they don't.
No,
share.
it's not that it doesn't hold. It's just there's no real bridge. But like if you take quantum mechanics, okay, the idea. This is basically the idea. You have quantum mechanics, and you can say things about particles and whatever. Now add more particles and zoom out. You don't get GR, which is what should happen, right? Because if you add more particles and you get bigger things, bigger objects that are just composed of quantum particles, if you were to just apply quantum mechanics to every single one of the particles and see what happens to the object as a whole, you don't get general relativity.
So that's the issue.
That's the issue.
That's very tough.
Like one doesn't lead to the other. And then obviously general relativity doesn't lead to quantum mechanics, because what does it say about particles, you know?
Well, like then that's the whole point of loop quantum gravity. So like,
well, I mean, I guess it does say something about particles, except you're not going to have something like a proton gravitationally bound to a proton, right? That doesn't happen.
That's
because at that scale, it's strong force and electro weak, strong, whatever.
So, I mean, what I, again, have heard from my knowledge is like loop quantum gravity is like trying to, or at least this theory is like trying to bridge that gap. Obviously, everyone kind of is. And him being a particle physicist himself, or kind of like more cosmologist himself, is trying to bridge this gap. And one of the things we were studying is, well, these equations of motion. So like the way we were doing it is kind of cool. Again, just hear my words and then maybe search it up, but like don't really, again. So the CGHS model, which is is basically four people. Again, their names are somewhere in my report, but I don't really remember it. So it's like the CGHS model is actually a really cool model. So general relativity is very complicated. Why? Because it's 3 + 1 dimensions, and a lot of things happen in 3 + 1 dimensions, like propagating gravity waves. Gravity waves is one of the biggest things that can only happen in 3 + 1 dimensions, and no other subsequent dimensions. But I think there's another way of viewing something that allows gravity waves. But anyways, so the CGHS model is basically general relativity, but 2-dimensional. So like 1 + 1D. So like one space and one time dimension. So basically it simplifies everything, but it still has like the intrinsic properties of what general relativity has to really offer. So what basically the task was or what we had to do was the CGHS model obviously had this, or not obviously, but had this thing called the action. I'm sure we've heard of it. So the action that described basically the motion of space dictated by this model in this scenario. So the scenario that we are dealing with, we're not near the black hole quite yet. But in this scenario, we're simply trying to understand, okay, how does this action deal with this whole situation? So here we have the action dictated by some crazy formula. Of course, not going to get into the actual math of it. The idea, however, is to take this value and compute some things. So what do we compute? We first compute the Lagrangian. We can directly get the Lagrangian from the action. Remember, the action is basically another way of saying these are all the potential paths of this object taking. So for example, in space, in spherically symmetric, like loop quantum gravity, like in space, how this object will move will be given by the action, all the different paths that it can take. So the Lagrangian, again, I'm sure we've spoken about this. We had a whole classical mechanics episode on this very topic, so I'm sure you're aware of the Lagrangian. But basically, the reason for doing the Lagrangian, conversion, is because of something called the Legendre Transformation. Now, I don't really know too much about the Legendre Transformation, but basically the idea is to take the Lagrangian and to convert it to something that all quantum mechanicists love, which is the Hamiltonian. Now, the Hamiltonian has multiple benefits in quantum mechanics and multiple benefits by itself. I think Parker and I were talking just before this, where the Hamiltonian primarily provides just easier math, and it basically allows us to do a lot of things at a much easier and much faster rate.
All right, I'm back. I have a few comments on what you said.
The Legendre Transformation?
No, okay, you said something about the action, that the action...
it's basically all the paths.
No, so the action is actually... there's a definition to the action.
Okay, like an actual definition.
The action is the integral of the Lagrangian.
Right, yeah. Well, I didn't say that.
Over some path.
Yeah.
Right?
Yeah.
And so the path that... Well...
it's the integral of the Lagrangian over the space. So it's like all the paths.
Well,
is the action.
It's a time integral, right?
Right,
it's
right,
dt.
exactly. It's a dt. So
from one time to another, right?
So it's all of the paths. That's what I'm saying. Right. That's the action, isn't it?
Well,
isn't that the action?
Well, it depends on the path. That's the thing.
Well, yeah.
The action depends on the path, and the idea is that the path that a particle will take is the path that minimizes the action.
Yeah, that's the Lagrangian, because the Lagrangian is the partial derivative of the action with time. So the one that minimizes that, right? Or
wait, the partial derivative of the action with time?
Because
oh, I guess
obviously, because the action is integral, right? So that's what I'm saying.
But
so wasn't that the whole thing?
But that's not related to, like, you're saying the action is all the paths.
Isn't that?
It's not.
Isn't
all
like the action telling you like where this thing can go?
The action.
Isn't that the idea of the action?
The action depends on the path that the particle takes, right? Because if a particle,
that's the Lagrangian, or am I getting them mixed up?
If a particle takes a certain path from time 0 to time 1, right, and you integrate over that path, you get a certain amount of action, right?
Yeah, then you get another action. So you're trying to.
But if you take a different path, you get a different action, right? So the one action is not associated to all the paths. One S is associated to the particle.
Action is more like just
over.
Telling you like how it can get there, but it's not telling you.
The action is basically just a quantity.
So what do you have to? But then so then you do have to minimize the Lagrangian, right?
No,
you minimize
you minimize the action to find the path.
So minimizing the action is just the variation that you're minimizing, right? So
yeah.
The way you do that. So then where does? Okay, so basically, what I've understood so far.
Yeah.
So the action you're saying, I mean, okay, yeah. Now that you put it that way, yeah, it would obviously be path dependent.
Because it's the principle of least action, right? The principle
of least action is the whole thing.
So you want to differentiate the action,
right,
with respect to the path.
Right, not T. Right. Right. You're trying to minimize
my throat is so dry right now.
Yeah, no, I feel that, man. That's crazy. Right. So better understanding of the action. Fantastic. You want to say anything about the Legendre transformation?
Oh, yeah.
Talking about that too.
Okay, so if anybody knows anything about the Lagrangian, the Euler-Lagrange equations give you, so for each generalized coordinate, there's one Euler-Lagrange equation. And these equations are second order in time. So you get, if you have n generalized coordinates, you get n second order differential equations that you have to solve. We all know that first order differential equations are easier. So even if you had more, they would be easier to solve. And so I'll say it like this. The Lagrangian is a function of the generalized coordinates and then the time derivatives of the generalized coordinates, and then also sometimes time. The Hamiltonian, however, is a function of the generalized coordinate and the generalized momentum of each generalized coordinate. Excuse me. And what happens is that the equations of motion have to do with the generalized momentum as well as the time derivative of the generalized momentum, but they happen to be first order equations of motion. However, you get two. You get one for p, which is the generalized momentum, and one for p dot, which is the time derivative, which makes two differential equations for each generalized coordinate, and you have n generalized coordinates. So you get 2n first order differential equations instead of n second order differential equations, which are easier to solve.
Which is easier to solve.
So that's why when you're doing systems, like you have a pendulum or whatever, it'll be easier to solve, even though it's not that hard to
if you convert it to
solve.
Hamiltonian.
Yeah, if you use Hamiltonian mechanics, it'll be, in theory, easier to solve.
That's dope.
Yeah, and the Legendre transformation is basically, the Hamiltonian is a function of I'll just say Q for the generalized coordinate, and then P for generalized momentum. So P is the partial derivative of the Lagrangian with respect to Q dot. And so what you're doing is you're just rewriting everything in terms of P instead of Q dot. And so once you switch all of those, then you get, boom, Hamiltonian.
Bang.
Well, actually, the Hamiltonian is defined as, like, there's a definition for the Hamiltonian, but in going from L to H, you replace all of those things, and there you go.
Bada bang.
Yeah.
That's how you get your Hamiltonian.
Yeah.
Well, once you have the Hamiltonian, what we did is we quote unquote quantized it. What does that mean? We basically took some variables that were part of the Hamiltonian, and we just converted them to their quantum parts. So we put some sines, some cosines, because, quantum mechanics loves its periodicities. So that's basically what we did. Now, once the Hamiltonian is quote unquote quantized, we have now basically transferred our interesting view, like our action in CGHS model, to now a Hamiltonian. With this Hamiltonian, we can now solve for the equations of motion of, the space variables. So there are two major sets of space variables. Now, I think in the actual episode with Dr. Rastigu, hopefully we have it soon, he'll explain more about what these variables actually are. I do have it somewhere, but again, I took it last year. So it basically, I'm kind of trying to remember it, but as I'm trying to remember it, I'm kind of forgetting it because basically it's a little complicated because there's one set of variables that's, let's say, subscript X, and the other set of variables subscript phi, because those are the actual subscripts that we use. And one of them basically describes, I'm trying to get the good definition, like the way space curves, and one of them describes the way, I'm trying to think about it, but they're basically different ways of saying basically how different parts of space move, right? Just say that. And as you were saying, so there are 3 generalized coordinates, I believe. Yes, I believe in a 1 + 1D, how many, I'm sure, I know in a 1 + 1D, how many generalized coordinates would they be? I kind of forget.
For a particle?
2? Yes.
Well, it depends on
doesn't it depend on degree of freedom?
Degrees of freedom.
Right. So
because each degree of freedom is one.
Right. In this case, there is
Probably 3.
In a 1+1, no, I was sure like in this that there was either like 0 or 1 degree of freedom, because like that was the whole advantage of using this model.
There can't be 0.
Well, not 0, but like no, there is actually 0 in like a model to like simplify it. I don't think it's this one, but
damn.
Anyways, as I mentioned, I'm not very proficient with this explanation because it's a little confusing to me as well. So even as I'm trying to explain it, it is a little confusing. So bear with me, and I'm sorry for all the listeners out there. But yeah, I'm trying to think of it as I'm trying to say it, and it's not fantastic. But again, basically what we did was, again, after we got this Hamiltonian, after we computed the Hamiltonian, we were like, okay, now let's solve the equations of motion. So the actual, what we were finding out was if we quantize it in different ways, what are our different results of equations of motion. So we actually tried different quantizations. We tried changing different variables multiple times. Again, I can't even really go into the depth of it because I don't myself understand the depth of what we changed. But I can tell you what variables we changed, but that's not really going to help anyone. So we changed multiple things basically to test out which, number one, equations of motion took the least amount of time to solve, because that was obviously a big one as well, because some actually took a little bit of time. And number two, which ones kind of looked the cleanest. Like, believe it or not, that was actually one of the things that we were looking for, simply look the cleanest. Because sometimes, again, what we were solving in, I should probably have said that. So we were using Maple, very similar to, what's it called? Mathematica. It's basically like a PDE, ODE solver. It's very, very proficient. And if you give it some real nasty stuff, it'll return some real nasty stuff, but it'll be right, hopefully. So yeah, obviously a lot of times that we got things wrong, we had to redo it. Obviously, this went over through a good part of the summer, so it was back and forth testing different ways to actually quantize the Hamiltonian. And obviously, these were inspired by reports. These were inspired by our own research and inspired by our own sometimes Google searches. Like, hey, listen, this is another way. So basically cumulative, again, as I mentioned, we didn't actually find, like, we didn't have like a final, this is the one, but it was kind of just, it was very entertaining to still solve all these different PDEs and trying to understand a little bit, because this is actually before I had even taken the PDE class. So I really didn't really understand what was happening, because it's still pretty cool in like high level, but very cool for me still, because I was definitely enjoying what I was learning, even though I didn't really understand too much of it. Still enjoyed most of it. So yeah, that was basically my last summer. I really thought I would talk a lot less on that last summer. I didn't expect to talk this much on it, but again, because it was a lot of computation, just mainly just test, trial, test, and that was most of it. But it was still a very nice wrap up that I had after, I wrote a nice report summarizing all the stuff that we had done. So it was really cool. I had a good refresher. And yeah, that was basically my last summer.
That's pretty cool.
Yeah. I think you want to talk about something, right? And then we can shoot back.
The second part of my summer, which had to do with data visualization mostly, was the bulk of my summer. It's what I made my final poster on, which I had to present to the fellow students and professors in the department. So what was the need for a student to work on this? Basically, the Dragonfly telescope brings in a lot of data, because instead of having one camera that takes pictures, you just have 48, just more. It's inherently just more data. And what happens is that, okay, the Dragonfly offers better performance in terms of capturing very dim objects. The trade-off in heightened performance is also heightened complexity. There's more things that can go wrong when you use this apparatus.
48 lenses, man.
Exactly.
Of course.
There's just more things that can go wrong.
Yeah.
And so the team, the Dragonfly team, needed essentially a dashboard that can be referred to for just upkeep and just a way to visualize all of the data coming in from the telescope. And so that's what I got started on immediately. I started getting used to the there was already a Python package that was written for data reduction. There's a whole data reduction pipeline that was created by the Dragonfly team specifically to deal with 48 light images, 48 flat fields, 48 dark images coming in, and then having to create master flats, master darks, correct everything, stitch everything together, and then produce a final night image. There was a whole process for that was already built. And so in order to kind of capture the essence of this process, I had to go through this whole boot camp where I would learn how the entire pipeline works. After that, I started learning about how to build an app, how to build a dashboard, and then I was left on my own, essentially, to figure out what features should go on the dashboard, what would be useful for people to, open the dashboard and immediately see information that would be pertinent to the daily researcher on the Dragonfly team. And so the first thing I thought about, and one thing that was a part of the data reduction pipeline, is associating flags to certain images. And flags correspond to simply a problem. And so for each type of image, there's a different number of categories that can arise. And these flags are stored in a binary number where each digit represents either no flag was raised, which is a 0, or a 1, which is this flag has been raised. And each position corresponds to a certain flag. For example, in the flat field images, sometimes you'd have the moon that would be in the sky. Or, sorry, not the flat field ones, the light images. The moon would be in the sky. And obviously when you're trying to capture an ultra diffuse galaxy and there's a super bright object that is in your field, you will basically be able to see nothing. And so those images will be trash. So noticing that the moon is in the frame and being able to flag that to say, you can immediately see, hey, the moon is up, trash these images. That is a pretty useful thing. And that is just one flag among many that can be raised in an image. And so one of the features that I added was a bar chart of all of the flags that have been raised. Just to be able to see immediately. You open up the dashboard, it loads up last night's data, and you see the bar chart, and it says there are 100 images that are corrupt. Immediately you can tell, boom, that was a bad night. Something went wrong. But now you need to think a little bit further. Now you see that, okay, there are a lot of flags that have been raised, but let's say you look a little bit deeper and you see, oh, there are 10 cameras on the Dragonfly array that have been performing very poorly. And by performing poorly, I mean flags have been raising every single night. The first step is, how do you know flags have been raised every single night on that camera? Well, there's an entire data frame with every single night, every single image from every single camera that's ever been taken. There's an entire data frame with all that information that is stored on Amazon, the Amazon servers. And so what I do is I import the data from the past, and you can change this number, but let's say 5 days. I import all this data, and what I can do is I can plot the performance of each camera during the past 5 days. Now you have a way of checking which cameras have been performing poorly, and also what is the track record of these cameras. Let's say you check and you see that one of these cameras has been performing poorly for 5 days in a row. So you know that this is a recurring issue. It's not just one night something went wrong. It was, the night there were clouds in the sky. Boom. Every camera has a bunch of flags that says we can't see anything. But the next night everything's fine. That is just a transient event. fine. But if one camera performs poorly 10 nights in a row and then every other camera is performing fine, the first thing that works well in your favor is that you can identify which camera is performing poorly.
Via the flag.
Sorry?
Via the flag.
Yeah, exactly. Right. But you know exactly which camera, which means that you can tell somebody that is in New Mexico, go fix this on this camera.
That's cool.
Right? So that is one thing.
Have you
no.
Next to someone in Mexico? No. This one ain't working, mate.
I haven't done that. But that is a use for the dashboard.
Yeah.
Now, the second idea is that the second idea is that you can essentially build a, how do I say this? Not only can you tell which camera has something wrong with it, you know exactly what it is, and then you have other people on the team who know how to deal with that issue. But the entire point of my project is not dealing with the issues. It's figuring out a way to organize the information coming in from the telescope and distributing that information to the people who need to have it.
What's the most common type of issue?
It could be anything.
The most common, like, have you actually run this on the telescope?
No, I have.
So what's the most common type of flag that you get?
But it changes, right? Oh, it changes, right?
Right.
It's
one. So it's not like one common thing that always happens. Oh, dead pixel.
No. It's
also 48 individual CCDs, obviously, right? Mm-hmm. Yeah, obviously. What am I saying?
Yeah.
And it's all circular.
Sorry?
No, that's a stupid question. Never mind.
Okay.
Stupid question.
So I'm trying to think about the other charts that I had. Oh yeah, right. So data visualization, I had a bunch of charts that were put up and a bunch of things that you could check about the telescope, about the cameras, about the performance of the telescope, etc. Now the idea is, how do you work in this dashboard to the workflow of the Dragonfly team? And we came up with creating a Slack bot.
Nice.
And so I spent about maybe like 3 weeks learning the Slack API and figuring out how to make a bot that will run the dashboard, will get the information from the dashboard, and will send it through Slack.
It took you 3 weeks
to figure out the Slack API.
Yeah, I can't even imagine. That must.
It is complicated.
Yeah, no, I can imagine.
It is complicated.
Yeah. I've dealt with API. It's annoying.
It's
I don't know what Slack is like, but by the way, Slack is a messaging platform for those of you that might not heard of Slack. Yeah. I don't know if it's.
You can send like messages to a group.
Yeah, but it's pretty business oriented, like very formal.
Business.
Like
it is a
business
formal
student. Like it's a very upkeep, very very organized.
Yeah.
Very high level messaging platform.
Yeah.
Yeah.
And so I had to figure out how to send messages, not only messages, but messages that contain the information that you wanted to see, right? So if I wanted to see the data from a specific night, how do I get the bot to spit that out on Slack?
Bot, I can be like, day this.
Yeah.
Nice.
And also, the bot also posts the images of the charts that you would see on the dashboard. And so you can actually tell the bot, there are a few commands. One command is just update, and update will take last night's data.
Nice.
And it will give you all the information that you need to know.
Yeah.
But just like the surface level information, if you want to know more, obviously, you'd have to go on the dashboard and see what's up over there.
Dashboard online or?
Yeah, it's online.
Is it like public?
I don't think it's public right now.
Is it like stuff via GitHub or something or what?
It's on GitHub. Like the code for it is on GitHub, but I don't think it's public. And also,
well, that's cool.
And also, even if you wanted to, you wouldn't be able to go and run that code from GitHub because you need access to a Python package.
Oh, which is only by you?
It's locked on a private repo which is owned by the Dragonfly team. So
why would they not let you?
well, they gave me access.
No, obviously, but I'm saying like, what would they not want the public to?
No, there's a lot of stuff on there that you don't want to be public.
Okay.
No, like there's like things that, you know, if you run a multi-million-dollar project, you don't want to just give everybody your source code, you know?
I guess you're kind of correct in that. Yeah, you're kind of correct in that.
Yeah.
I see that. Well, that's pretty cool, man. So that was kind of like a conclusion to your...
Yeah, so that's... I finished the Slack bot, and then I made my presentation. I gave the presentation, and then the last few days, I just put everything on GitHub. Well, I was putting it on GitHub throughout the year, except I wasn't really paying attention to it. So I made some nice README files for those repos so that people can go in and not be confused.
Not be confused. That's cool. Well, that's fantastic. Kind of a wrap up to your summer.
Yeah.
So I think I can just like brush over maybe what I did this summer. Again, not as intense whatsoever, but it was, as I said, more relaxed, more fun.
Mm-hmm.
So I joined the aerospace team at U of T. Really cool team. They have a bunch of subsections. They have like a space subsystems. So if you wanted to work for like, for example, they're launching a satellite this year. So that's pretty cool. Brett, our friend who is also on the podcast, is actually working on it, which is pretty cool. Yeah, because he knows like GIS with like surveying software, and like not anyone else does. So he's gonna help him out, which is really cool. Then there's another subsection which is propulsion. Rocketry, where I am. There's another one which is, I forget. Damn, this is bad. There's another subsection that I forget, but basically, I was really interested in rocketry. I've always been interested in rockets. I mean, which kid interested in science isn't? Or at least that's how I thought.
Yeah.
So, yeah.
I actually wasn't that interested in rockets.
Well, damn. So I think I've told my history of Kerbal Space Program on this podcast before. So that definitely ignited, pun intended, my interest into rockets. So, yeah, I got on that team, you know, started doing some cool stuff, just getting involved a little bit into, you know, what they're really doing, just a little understanding of, you know, what the team does. And they do a lot of things, believe me. Every single part, like there's a subpart to a subpart to a subpart, and that person probably has someone doing something for them. So it's like that deep because everyone has something to do, and there's always something to do. For example, this year they launched their first hybrid rocket. Very, very proud to say, again, I wasn't a part of this, but very proud to say that they were the first Canadian school to launch a hybrid rocket, I think.
Wow.
Yeah. Or, yes. First Canadian school to launch a hybrid. Or first Canadian school to do something big, and I'm 99% sure it's launch a hybrid rocket. So, anyway, not 100% sure, but I'm pretty sure it's to launch a hybrid rocket. So yeah. A lot about rockets. What I did was we actually built our own rockets, much smaller, about 1 meter high, like model rockets, basically. This is to get our L1 certification. I think I've spoken about this before. It's basically a certificate that says, hey, you've flown a rocket before, but number 2, it allows you to buy a certain class of rocket motor and up for your own recreational flying. Obviously, if you go in select areas, but if you want to just fly a rocket, for example, and I wanted to buy an H motor, I would need to be like H or an I motor. I would need to be L1 certified. So there's a limit. Obviously, I'm sure that makes sense, right? Like basically after a certain amount of thrust, you need to be, but like, okay, I know what I'm doing here. So making the rocket was really fun. Spent a good, a month, 2 months on it. I don't know if I've spoken about it on the podcast, but I should definitely show it on the podcast one time. It's really cool. Painted it Ferrari colors, so it's really sick. Really, really sick. A lot of sanding. Remember, whenever you're making a model rocket, for those of you that have made a model rocket, definitely enjoy the sanding. I have made my own set of smaller ones before, but never anything so big. So basics with rockets, I think we can just go over just like a little basics. I think like the most important thing about rockets is just understanding a little bit about how they work. For example, like, you know, why are there fins? Or Some rockets don't have fins, you know. So you may be asking yourself that question. Some are solid rockets, some are hybrid rockets, some are liquid rockets, all these different names. So we launched solid rockets. Solid is the easiest. It's usually aluminum, like a mixture of aluminum or like ammonium perchlorate, or it's basically just like the solid mixture that when you basically run this electrical charge from far away, and you just run an electrical charge that just kind of heats it up, basically creates like a large temperature differential. So it just forces the grain or whatever the actual material is to combust, and then you have like this nose cone like combustion chamber that kind of, you know, juts all the combusted material out, and that basically makes your solid rocket motor. So that was pretty cool, learning a little bit about, you know, because we actually got to use it this time, a little bit about how the delay charge works. Because remember, when it's up there, it's not just going to float down, right? Like, it's going to be coming down at terminal velocity. I don't know if it comes down at terminal velocity. Maybe not terminal, but it's still pretty fast. And
there's a lot of, because it's light, right?
Because it is light, that's what I'm saying. So it's not like really that, it's cardboard after all, right? It's not really terrible. But yeah, it's still coming down fast, so you want a parachute. But when do you launch the parachute? So you got to wait for a little bit. So
is it remote? A
little theory. No. It's a delay charge. So what we did is we kind of tested some of our other people's rockets to see how long we would have to wait. It was pretty bad, but that's the best way to do it, right? So what you want to do is... of course. Like, our simulation set a certain amount of time, but the simulations are not always one-to-one accurate.
You might want to add a little bit more.
That's what I'm. No, usually we want to. Well, yeah, because you never want to subtract, because you never want it to go off apogee, right? Yeah. So your ideal parachute position or parachute deployment for this size rocket. Remember, for this size rocket, if you have a bigger rocket, then you have like a drogue parachute and like a bigger one, and that's a little bit different. for like a smaller size rocket. After apogee, which is like highest point in the orbit, I don't think it's at apogee. Or is it at apogee? All right, I think it's like a few seconds. Yeah. Because, so motor burnout occurs at X, right? Then apogee occurs a little bit after. So I think, ideally you want to get it at apogee. Why? Because your velocity is the lowest. I'm assuming that's why you would want to get it at apogee. So the deployment of your chute, theoretically, should be the safest. So again, after the motor burns out, there's this delay charge. So from the time that your motor starts burning, there's another. Oh, by the way, important thing about a motor. Really cool way that a motor works. You might think, I don't know. I'm just adding a few things of knowledge that I have from here and there. As the motor runs out of, propellant, right? The center of mass of that motor is changing. And therefore, the center of mass of your rocket is also changing. Now, one very important thing about stability, rocket stability. This is like Rocket 101, basics of lift. I think we've said this before, but the center of pressure or the center of lift has to always be behind or like downwind of your center of mass. That kind of makes sense, right? Because remember, it's always rotating about the center of mass. So if you have your thrusters at the bottom here, it's going to want to rotate. How do I say this for audio? It's going to want to rotate upwind, like because your thrusters are pointing upwind. So if your center of pressure, which is basically the center at which all the aerodynamic forces are acting, basically, like your center of lift, if your center of lift is behind the center of mass, then it's literally going to be counteracting that torque because the booster is going to want to force it upwind, but because the wind is going down and because the center of pressure is behind the center of mass, it's going to kind of stabilize itself. I don't know how good of an explanation that was. Hopefully that was decent. But basically a core tip or a core rule, not even tip, rule in rockets is if you want a stable rocket, or stability is literally defined as the distance from the center of mass to the center of pressure. So center of mass, always being in front. If it's not, it's negative, and then you have negative stability. So then it doesn't work. Rocket literally just won't fly. So it's the center of mass minus the center of pressure over the diameter of the rocket. So that's basically giving your stability factor. So the larger the diameter of your rocket, the smaller the stability. But the larger the distance between your center of mass and center of pressure, the larger your stability. So stability is like one of the most important things in all of aerodynamics because that's basically how things fly, right? Even with planes. Now, there was a rumor, or I don't know if it's a rumor, but like there was a thing where like the engines are placed ahead. Like, you know how engines are in like planes are like ahead of the wings, like very clearly ahead. My original, now correct me if I'm wrong, but I always originally thought that it was because of this whole thing, because the center of mass has to be ahead. Has to be ahead of center of lift. So if the engines, which are obviously much heavier than the wings, are ahead of the wings, that means again upwind of the wings, then it should be stable. But I don't actually think it's because of that. I read somewhere that that's not true. So if someone wants to do some research and put it in the comments or shoot us a DM, I would be very interested in knowing if this thing is actually true. But again, center of mass, center of lift, core thing in all of aerodynamics. That's a cool thing that I learned this summer. Then, as I was saying with the rocket motor, sorry, I'm going everywhere. But as the rocket motor is burning, there are multiple pellets that actually burn. It's not just one huge thing. Why? Because if the one huge thing burned, then the center of mass would be changing quite rapidly, right? Because the motor is quite heavy in regards to, I mean, not quite heavy, but it's significantly heavy, especially when you're dealing with a cardboard rocket. So when you're dealing with this rocket and the motor is starting to burn all this propellant, the center of mass is increasingly going downwind. So closer and closer to the center of pressure, and therefore less and less stable. So that is why there are actually multiple different pellets in all of these solid rocket motors, and they burn at the same time. So the way that the charge is ignited is, think about two different cylindrical blocks. There are actually three in the one that we launched, but think about two cylindrical blocks. If they're both ignited at the same time, the center of mass difference, then igniting the whole thing, is much less. So in total, the stability is somewhat preserved because obviously, eventually, it is going to drain. So we have to think about that. So eventually, as the solid motor completely drains, we have to make sure that the center of mass is still very much ahead of the center of pressure. So that's like Aero 101 that, well, I didn't really learn it this year, but I guess like I applied it this year. So that was really cool. And a bunch of more UTAT stuff. I'm more into UTAT this year, or UTAT being the aerospace team. So let's see how that goes. But mainly just a cool set of rocket stuff. We went all the way to New York to launch it. Really sad story, but I'm not gonna get into it right now. But we went all the way to New York to launch it. It was a lot of fun, super experience. And in October, we're actually going to be launching our L2s, which is, well, a bigger motor. Yep. So that's going to be fun.
Cool.
So yeah, that's basically our summers. I think that wrapped up most of it.
Yeah.
We've been talking for quite a while. We haven't done this in quite a while. Mm-hmm. So it's been an interesting experience.
We're going to try to get a podcast out next week as well.
So we're committing to weekly.
I think we'll try weekly. We'll try
weekly. See, school hasn't started yet. So, I mean, it has.
We ain't kind of started.
It has actually fully. I just had some assignments to do like this whole week. But school has definitely started, but it hasn't really. You know what I mean? Like the assignments haven't really gotten crazy.
I don't know. We'll see.
So we'll see. For now, I think we'll release it weekly if possible.
Yeah.
Yes. Like our schedule is weekly, but if it's not weekly, don't get annoyed because it might just be because we're busy.
Yep.
So there's that.
Well, everybody who has listened to this podcast, thank you for listening to this episode. This is 107.
Wow.
107 episodes. Thank you so much to everybody. Make sure to follow on Spotify and rate 5 stars.
Why not?
Why not? Leave a 5-star review.
We love those reviews.
They're nice to see.
Love them.
Other than that, subscribe. Maybe leave a comment if you want to be the comment of the week. And yeah. So yeah, I guess thank you for listening. I'm your host, Parker.
And I'm Ray. And we'll see you soon.
Bye, guys.